Thanks very much. So today I'm going to be talking about some ongoing research that our group has been doing at quantifying uncertainty in hydrological predictions. And I want to provide a couple of key messages here. Firstly, I want to illustrate why it's important to consider predictive uncertainty in decision making. And secondly, I want to demonstrate that it's not particularly as difficult to generate these predictions as one might think. So predictions from hydrological models are commonly used to inform management decisions. These could be models that look at estimating flood risks. They could be models for looking at environmental flows. Now, these hydrological models often have highly varying predictive capabilities. So this figure here shows in red some observed stream flow, and in black is some simulated stream flow from a rainfall runoff model. And we see that there's quite large differences in many cases between the observed and the simulated responses. So that's what we see down the bottom here. This is the difference between the two time series. And these errors can be due to different sources of uncertainty. It could be because a rainfall event was missed by a rain gauge. It could be due to a process being missed from the hydrological model. So being able to understand and quantify the uncertainty in these predictions is really critical for reliable risk assessment and for robust operational applications. So I'm going to start with a little illustration about why it's important to consider uncertainty in decision making. And what we're going to be looking at is a couple of actions, action A in red and action B in green. And on the x-axis here, we're looking at some measure of system performance. This could be stream health, it could be drought resilience, it could be flood safety. And what we want to avoid is a performance failure, which is given by this dashed line here. Now, if we don't consider any uncertainty in our predictions, we're going to choose the best outcome. This is the outcome of action B, which is furthest away from our performance failure. But sometimes there might be cases where if we consider uncertainty in our predictions, we might come away with a different outcome. So, for example, for these two distributions here, for action A and action B, if we're risk averse, we might end up choosing the action with the lowest probability of failure. And this is now given by this red line here. This is corresponding to action A. So depending on whether we include uncertainty or not in our decisions, it's going to be really important. So our group and the research that we do is all about making good probabilistic predictions for hydrological modelling. And before we get into how we do this, I'd just like to talk a bit about what we mean by good probabilistic predictions. And these predictions are going to be most valuable to users if these are what we call reliable and sharp. Now, a prediction is going to be reliable if it's statistically consistent with the observed data, whereas a prediction is sharp if there's small uncertainty in these predictions. And I'm going to be talking about these terms throughout this presentation, so I'm going to give a few demonstrations about what I mean by reliable and sharp probabilistic predictions. In these figures, we have time on the x-axis, we have flow on the y-axis. It could be any environmental here on the y-axis. And we're looking at these white dots here. These are our observations. The yellow band corresponds to a 90% probability limit. Orange bands are 50% probability limits. And in this example here on the left, we have predictions which are reliable, but they're not sharp. So they're reliable because 10% of the data lies outside our 90% confidence limits. Similarly for our 50% limits as well. But these are particularly wide distributions here. So there's not much information that's being gained. So if you're going to use a prediction like this, you're going to make conservative decisions. You're probably going to overestimate your risks, and this might lead to missed opportunities for cost saving. Another problem that we can have with our predictions is they might be sharp, but not reliable. So this panel here in the middle shows some predictions where we have narrow limits, but we see that in this case, a lot of our observations lie outside of our predictive limits. And that's also a problem. So here we're going to be overconfident. We're going to underestimate our risks. And this means that we won't probably be able to manage our high and low flow events. Now what we want is to have predictions which are reliable and sharp. So that's what we see here on the right-hand side. And this is going to allow us to make better management decisions, and it's going to be, allow these to be based on better estimates of risks. Now, there's a range of methods that have been used to generate probabilistic predictions of stream flow. But until recently, there hasn't really been a wide comparison or a comprehensive comparison between different approaches for estimating uncertainty in predictions. So what we did in a recent study, published last year in Water Resources Research, was to compare a wide range of approaches, different residual error models that have been used to quantify uncertainty in hydrological predictions. And what we wanted to do was we wanted to evaluate the performance of these different error models over a wide range of catchments. We looked at catchments from Australia and the US. We wanted to look at a range of different performance metrics, such as reliability and sharpness, and we wanted to consider multiple hydrological models to make sure our conclusions were robust. And based on these findings, what we were able to do was provide some recommendations on which simplified practical approaches to use to quantify predictive uncertainty. And we found that by selecting certain approaches, we were able to improve both the reliability and sharpness of our predictions. So an example of this is given by these predictive time series down the bottom. On the left-hand side, we show some time series or some predictions which have been generated using a weighted least squares approach to estimating uncertainty. And for this particular catchment, we found that we had predictions that had poor reliability and poor sharpness. Now, when we implemented a different approach to representing uncertainty, this was namely the Box-Cox transformation with a fixed transformation parameter of 0.2, we were able to both improve the reliability and the sharpness of our predictions. Now, what's been really pleasing about this work is that now these recommendations are starting to be used by colleagues in industry. An example of this is with the Bureau of Meteorology. Their seasonal streamflow forecasting service has operationalised some of the research findings that we've made. The Bureau's seasonal streamflow forecasting service provides monthly forecasts at about 200 locations around Australia. If you go to their website, you can see these purple dots. If you click on those, you can get some forecasts for stream flow in the coming months and seasons for approximately 200 locations around Australia. And our group's had a long-term partnership with the Bureau, their water forecasting team, and over this time we've been able to provide reliable and sharp monthly streamflow forecasts across Australia. Now, one of the biggest improvements has come from our findings from our previous study on comparing different approaches to estimating uncertainty. And what we've managed to do is improve the reliability and sharpness of our forecasts at a wide range of locations around Australia. On the left-hand side is we have forecast skill using the previous approach to estimating uncertainty, and on the right we have forecast skill after they implemented our recommendations. And what we see here, these different dots correspond to different catchments around Australia, and the colour corresponds to different forecast skill. So red is low forecast skill, where we have poor reliability and sharpness. The green is high forecast skill, where we have much better reliability and sharpness. And we can see that by implementing our recommendations, we've been able to increase the number of sites around Australia with high forecast skill from about 20% up to more than 80%. So that's been a big finding with the Bureau. So far, I've been mainly focusing on the uncertainty in streamflow predictions and forecasts. But when it comes to environmental decision making, what we're really interested in is not just the uncertainty in the hydrological predictions, but also the uncertainty in the environmental responses. So that's the next thing that we're going to be touching on here. It's known that the flow regime, so particularly low flows, are really important for ecological health of streams. Hydrological models and environmental response models are often used to assess different management alternatives for improving ecological health. Now, if we have uncertainty in our hydrological predictions, there's going to be uncertainty in the ecological responses to these different management decisions. So what we're looking at is, what we're wondering is, how is this going to impact on decision making? This question was explored by an honours group at the University of Adelaide last year. It was supervised by Mark Thayer, and we had colleagues at JUNA that were helping with this. And this group did a case study of the Barossa Valley region. They looked at the health of mountain galaxious fish, which is related to the number of low flow days in the catchment. And the group looked at 3 different management options of doing nothing, adding low flow bypasses to dams, and removing dams and extractions. And they compared the impact of uncertainty at the different sites. Now, what they found was the importance of the uncertainty was very different at different sites. At the top here, we're looking at some distributions of the probability of extremely poor fish health. And we see in the orange and blue, this is the options of adding low flow bypasses and doing nothing, that there's a significant amount of overlap between these distributions. So this says that the effect of management actions is fairly small compared with our uncertainty. However, at a different location, Mount Mackenzie, we see that there's far less overlap between these distributions. So the uncertainty analysis here helps to confirm the effect of the management actions. So what we've found is that while probabilistic predictions are commonly used in research, they're less used in industry. So what we want to do is make it easier for people to be able to generate probabilistic predictions and then use these in their decision making. And to do this, what we've done is develop a simplified approach to producing probabilistic predictions. We've got a paper hopefully coming out soon in environmental modelling and software. And what we've done is we've developed a web app. This is with Bree Bennett at the University of Adelaide. And we've developed a web app which allows people to generate probabilistic predictions. So the inputs to this app are simulations from a calibrated hydrological model and observed streamflow time series. And the outputs of this web app are a time series of probabilistic predictions. So we take as inputs the deterministic predictions and provide outputs as probabilistic predictions that can then be used to enhance your decision making. Now, this can be found at www.probabilisticpredictions.org. At the moment, we're looking for a small group of industry users that would be interested in trialling this web app. Hopefully, I've convinced you of the importance of probabilistic predictions in decision making. So if you get a chance to have a look at this web app, if you have some feedback about what additional features you'd like added, we can work on that. So in summary, hopefully I've convinced you that quantifying uncertainty in hydrological predictions is important for decision making. Some of the research that we've done at the University of Adelaide has helped to improve probabilistic streamflow predictions. This research has been utilised by industry users, the Bureau of Meteorology and now JUNA. And hopefully I've convinced you that simple and practical techniques that we've developed here are valuable, and this will enhance probabilistic predictions in decision making. Okay, thank you very much. If you want to find more details about any of these slides, have a chat to me after this talk if you like, or email me. And if you're interested in using the web app and trialling a simplified approach to predictions, please get in contact with me as well. Okay, thank you.